Up next, we have Git, not just for source code anymore. Josh Triplett is currently working at Intel, making Linux more awesome. I'll pass it on to Josh now.
Thank you. So, I'm Josh Triplett, and I think Git is awesome. In fact, I think Git is a lot more awesome than people give it credit for. When Git was first created, it was often described as a content addressable file system. The problem with that is nobody really knew what that meant. So when you were trying to pitch it as a version control system, but it officially described itself as a content addressable file system, what is this? So, you know, all the people who are good at marketing as opposed to programming said, well, let's throw that name away and call it a distributed version control system. That we can actually sell to people. But the talk I'm giving today is a lot more about Git's history as a content addressable file system than about its version control properties. So I want to give a bit of background on Git and what pieces of it are more relevant for using it programmatically as a data store, dig a little bit more into the repository internals than you might have seen before, take a look at some existing programmatic applications of Git for something other than just source code or even just text files, take a look at a few of the Git libraries you can use so that you don't just have to fork and exec the command line tools, and then go through a case study of a Git-based build system that I wrote. So Git has, as a data store, various nice properties, the most obvious of which is it's versioned. It stores multiple versions of objects. Okay, it's a version control system. That one was a gimme. It's distributed, which in practice, the important detail is that every repository is self-contained and has full history. You don't need a server, you don't need a local daemon, you just have a pile of files on your disk, so it's useful as a data store. It's content addressable, which in practice means you can look content up by its hash. So if nowadays key value stores are really popular, well, Git is a key value store. It's delta compressed, which means that you can store a giant number of copies of very similar data and it will use relatively little additional space. It's easy to poke around in manually because oddly enough there's this pile of command line tools associated with this data store that people seem to find very useful. And it's fully buzzword compliant, of course. It's NoSQL, it is fully cloud enabled, it's peer-to-peer, and it's social. So obviously you should have no trouble selling this to the folks who authorize what data store you're using for your next application. So I want to go through a few basic Git commands that you're probably already familiar with. The key thing is you really don't need advanced experience with Git to use Git as a programmatic data store. If you already know how to create a repository, how to add and remove content, how to commit things to your repository, how to create branches and tags, and how to push and pull data around, you've pretty much got everything you need covered. The big thing, though, is you really want to start thinking in terms of repository internals, not in terms of the high-level Git commands you're running. This is actually good advice for getting better with Git in general, whether you're using it programmatically or not. I've found, at least, that if you know what the underlying object store is doing, then you start thinking, what Git command do I run to make this change to the underlying state? Works very nicely. So repository internals for Git, at least the 10,000-foot view, are very simple. There are 4 types of objects that are stored in the repository, and then 1 type of metadata that references those objects. So the 4 types of objects you care about are blobs, trees, commits, and tags. And the one other thing you're going to deal with a lot when you're dealing with this programmatically is refs, which point to commits or tags. So let's go through these in roughly reverse order because they tend to drill down lower level from the top. So a ref can point to either a tag, which points to a commit, or it can point directly to a commit. It'll point to a tag when it's something in refs tags, whatever name. It'll point to a commit when it's something in refs heads, like a branch. So to use the Linux kernel as an example, if we show the refs tags v3.7, and normally this is just a file in .git, but sometimes it is stored all in one giant file that contains all of your refs because Git wants to make your life more difficult. But it's actually a nice efficiency thing when you have hundreds of thousands of branches, which you might actually do. So this is really handy in general for mapping arbitrary keys to tags and commits. If you want to create a key value store on top of Git that's using as keys something other than hashes, what you probably want to do is use refs to point at your commits and tags. But it's also critical for using Git programmatically, because anything that is not reachable from a ref in the Git repository will get garbage collected. And so rather than trying to disable garbage collection, it's a lot better to just create refs that point to your objects. Git does not listen when you say, "I'm not quite dead yet." So tags then they always point to a commit. And if you use git file-p is not a command you really need to remember for everyday use, but if you really want to show a raw object as opposed to something like git show, which will try to be all friendly about it, then here I'm just showing the same hash that we got from the previous slide of what the v3.7 tag is. So v3.7 is just pointing at a commit with this particular hash marked by object. It has a name, it has a person who tagged it and a timestamp, it has a message, and it's got a signature, which I left out for space. You don't have to have the signature in it, and for a lot of programmatic uses you probably won't bother, but that's the full content of a tag. So then a commit is just a hashed object, again, that contains a tree reference and a parent commit for every commit other than the very first one in your repository. So this creates a nice little graph of commits that even for programmatic use, quite frequently you're just going to have a linear chain of commits, but you can create arbitrary topologies here. But you've got a little bit of metadata, you've got who wrote the commit, you've got who actually did the commit, again you have a message. And then if you take that tree hash, trees just contain trees and blobs, and that happens recursively. So just like a file system, think of directories and files, trees and blobs, they map very nicely. So if you show the tree, what you get is a mode, which in practice you'll only ever see one of 2 or 3 different values here. One indicates a tree and one indicates a blob. You'll see a effectively redundant text indicator for a tree and a blob. You get a hash, and you get the file name. So this is the top level of that same commit tree. And if you look at one of those hashes for a blob, what you get is just raw content of that blob. So that's the main 4 objects and refs that you're going to care about for digging into a repository. So when you're dealing with programmatic access, the very first thing you're going to want to figure out is how your concepts, how your application's concepts map onto Git's repository internals. And the other key detail, again, is make sure you reference all of your objects, because you might not otherwise have a reason to. So with programmatic access in mind, one of the most common things people mention when they say that they're using Git for something unusual is that they put their home directory in Git, which this is really awesome. I highly recommend it, but it really isn't that unusual anymore. There's a lot of people doing it. You can search for it on GitHub. Actually, a friend of mine pointed out that now that they have a search for file names, it's fun to search for things like .ssh/id_RSA and see how many people forgot to exclude that. Yes, indeed. So the key thing is that when you're putting your home directory in Git, all you're really doing is using a bunch of Git commands. You're not using programmatic access, and half of what you're storing is really text files, but even if you're storing binary databases like gconf or dconf, you're still not doing anything all that interesting from a programmatic point of view. To make it slightly more interesting, you have something like etckeeper, which is tracking your system-wide Etsy directory in Git. Now this is a lot more interesting from a programmatic point of view, not because of what it's storing, but because of how it does it. It actually has hooks for distribution package managers like apt, and when you run something like apt-get install, it will notice, hey, the packages you just installed with these versions added these 5 new config files, so I'm going to automatically commit those and with a commit message that says you installed these 5 packages, removed these, upgraded these. So it's actually using Git programmatically. It's not just making you run the Git commands. It also has some hooks to track ownership and permissions, because Git doesn't. This is something you should keep in mind for your data store if you're storing things like Etsy Shadow. Or it turns out sudo is really picky about the permissions on Etsy sudoers. Another fun one is Git-backed wikis. Well, if you're building version control effectively, why are you doing it on top of a database rather than a version control system? You look at something like MediaWiki, and it's actually building version control on top of SQL. Ow? Just check in your wiki text into a Git repository, And the nice thing about this is for free, you get the ability to not just edit by web, which is actually now the harder case because you have to go run Git commands from a CGI, but you can edit by Git push. Just push new content to the wiki and have it render from a hook. So the original example of this was IkiWiki, which is quite awesome. I'd still recommend it. It inspired quite a few more, including GitHub Pages, which is probably the most popular at this point, and several dozen more because people have caught on to the fact that, hey, version control is the thing you should use when you're using version control. Go figure. Another fun one that's a little bit more orthogonal to the underlying repository is GitAnnex. And GitAnnex has, which I should give a blatant plug here, by the way, GitAnnex is also being presented at this conference, and I would highly recommend going to that talk as well. But GitAnnex tracks file locations without actually tracking the files. And there are a couple of reasons you might want to do this. The biggest one is that you can track really huge files without actually having any historical overhead. So if you've changed a file multiple times, or if you've moved it around to 27 different places, then you won't have gigabytes worth of files just because you've moved around a few 100 megabyte images. So the fun thing is that, first of all, GitAnnex uses a trick of checking in, effectively dangling symlinks. So it'll symlink off to another directory that's outside the Git repository that it fills in, and then it remembers the location of all the remote files that you have stored on other machines. And this is the fun bit about using Git programmatically. It stores that state in another Git branch, and it has some programmatic merge drivers for Git that know how to merge together the logs of where your files have been over time. You don't actually have to see this if you're running GitAnnex from the command line. It just does it all automatically and internally. And it has other fun features like encryption and a Dropbox replacement. And one other fun common theme you might notice is IkiWiki, EtsyKeeper, and GitAnnex were all written by the same person, Joey Hess, who's sitting in the audience. Awesome things done by Git. So another good one is Gerrit, which you may be familiar with if you've worked with Android or Chrome OS or a few other projects now. It's a patch review and repository management tool. So for repository management, it does a lot of the same things as GitHub or Gitorious. You can make repositories from a web interface, and then you can upload patches and do review of them. And from that perspective, it's not really obvious that it's using Git programmatically, though. But a couple of things it's doing. First of all, it tracks all of your repository metadata in Git branches. So if you make a repository and say, okay, these groups and these people have permission to push these particular tags and heads and do these things, it will actually keep that in a text file checked in on a branch. And you can, when you change it, you can add a commit message and add a new version of that metadata. You can roll it back. You've got full version control because, hey, it's Git. You get that for free. So why not? Something to think about for your programmatic application. Even if you don't have a use for versioning, go ahead and version your data because, hey, having the historical data means you've got free backups and free logging of what you are doing. It also implements some magic remotes. So when you push to Gerrit as a server, when you push to something like refs for master, it will put things up for review, create a page for every commit. It actually implements the Git remote protocol itself so that it doesn't really create a branch when you do this. It just extracts all the data you're sending it and puts it up in a temporary location so that you can review it. It also does other crazy things, like it's all implemented in Java. Okay, yeah, that's a crazy thing too. And it uses JGit, which is a re-implementation of the Git protocol, and it re-implements SSH in Java, which is a little bit crazy, but it's hard to do otherwise. So that's a nice introduction to there are various ways to use Git programmatically with various libraries other than using fork and exec. Now, after hearing the early part of this talk or other references for how Git repositories are structured, you might be really tempted to directly write Git objects to the repository because, hey, there's only 4 types of them. The formats are reasonably well documented. Yeah, don't do that. There are way too many corner cases, and unlike a lot of times, all of those corner cases matter and are used in real repositories. So there are things like packs, there are packed refs, there are remote protocols, there are several dozen weird little corner cases that you have to implement every single one before you can interoperate with real-world tools. And even after you've done all of that, if you get that far without saying, well, that was a fun experiment and throwing it away, you'll still end up with something that's probably a lot slower than actually forking and execing Git, even counting the overhead. So don't do that. The three alternatives that do make sense to use programmatically, you can fork and exec Git, you can use JGit, which is a Java reimplementation of Git, or you can use libgit2, which is a C implementation. So fork and exec is probably the easiest is not the right word, but it's the most straightforward. You run existing Git commands available from the command line, you parse their output and exit code, and the overhead of fork and exec is really not that bad for a lot of the high-level Git commands. So if you're running something like clone or push or pull, or even something like checkout, the number of operations you're doing inside that command are so many and so high overhead, or they're blocked on the network or the disk, that the overhead of doing fork and exec is really not that important. Where that really gets annoying is if you're trying to access individual objects. So if you want to read a commit and then read the tree inside of that and then recurse down to get to a file that's 5 levels deep, it's really painful to use git cat file and fork and exec that. Or if you try to use something like the streaming batch protocol where you send it something and read the data back on a pipe, it's really hard to get that right. It's painful. On top of that, it's really hard to handle errors well. You end up with something that feels a lot like one of those kids' toys that tells you what the animal sounds are. The cow says, moo. Git checkout says, you are in detached head state. Yeah, it'd be nice to actually parse that and say, okay, really what's going on is this. Because if you're running a GUI app, there's always that point when you realize, oh, this GUI app is forking and execing command line tools. I know that because it wasn't able to do sensible error handling. It just spit up a giant dialog box with the command line transcript. So one of the better alternatives is JGit. It's a Java reimplementation of most of the internals of the Git library that ships with Git. It was written by several prominent contributors to the original Git toolkit, so it's actually fairly complete. But you are still going to need fork and exec occasionally when you use it because it doesn't do absolutely everything. It does cover a lot of cases, and it's used in various popular tools. Gerrit is one of them. It's also used for Eclipse and a few other things written in Java. The one that's becoming a lot more popular is libgit2, and it's written in C, and so it's obviously usable as a C library, but the much more important thing is that as a C library, it was designed with foreign function interfaces in mind, so it has bindings for a dozen different languages, and it's pretty easy to add one for your language of choice. So it also has really excellent documentation, and the main thing with it, though, is it's still not complete, but it's actually being worked on. You do occasionally need fork and exec, but they're pretty responsive to bugs saying, hey, it doesn't do this, so I had to run this command. It also doesn't always run as fast as Git, but that's a pretty high bar. It runs fairly fast, just not as fast as code written by people who know the inside of the file system because they wrote it. But they also tend to fix that over time, and the nice detail about libgit2 is that the low-level object access for blobs, trees, commits, tags, and refs is fairly complete. Actually, it's extremely complete. It was one of the first things that was written, and that access is pretty much as fast as it can be. So that complements the high-level Git commands very nicely. It means that if you want to use libgit2 as your low-level object access and use high-level Git commands via fork and exec, that works very nicely together. You have cases where each thing you want to do is as fast as it needs to be. And you can replace incrementally your use of fork and exec of Git commands with libgit2 over time. So that would be my recommendation. Use both and fall back to the Git commands whenever you find that libgit2 is either slow or incomplete. So with those programmatic access methods in mind, I'm going to go through a couple of signs that Git is probably the right data store for your next application, web app or local desktop app or whatever it is you're trying to build. First of all, if you have some notion of versioning, then obviously a version control system is a nice choice. Now, you may already have a built-in notion of versioning because you're building something like a wiki or something else where edits over time tend to happen. But even if you don't, then keeping historical records is something you might want to do anyway. You also want to get some benefit out of Git's ability to do deduplication or delta compression. So one big detail there is don't compress data before you commit it to Git. Don't commit .gz files or zlib compressed data streams. Just put it in Git. Git will take care of that for you, but it can then see inside the object and do delta compression against it. So if you store 1,000 copies of more or less the same file and it's compressed, you'll use 1,000 times as much data. Decompress it and you will actually use almost 1,000 times less data. The other case is if you're actually moving data around, then don't implement your own protocol for this. Build on top of Git's protocol. Use fetch, pull, and push. And you can either use the Git protocol, you can use the SSH transport, or you can even implement your own transport of choice, but you can route the Git remote protocol on top of that. So it's really easy to push objects between repositories and use that as your synchronization mechanism. So hey, you get network for free. Now, one big caveat is your tracked data should not be insanely huge. But remember, I just said tracked data. The lesson from Git Annex is if you have insanely huge data, then don't track that, track the metadata of that. So there are ways to work around this, but in general, if you're thinking you're going to be shoving gigabytes or hundreds of gigabytes or terabytes of data through this, you may want to pick another object store. Then again, it's not like SQL does hugely well with terabytes worth of data in one database either. Now, the one really big one is you should not be expecting to do complex queries here. There is no select from commits where author equals. You're just going to be doing lookups by a key. Pretty much any kind of unusual query, you're probably going to have to build your own index or hash or external lookup for this. You can use refs as your key value store for that, but in general, you should be expecting that the most common operation is to look something up by some key. And finally, you should probably have some use for content addressability by hash. So you want to be able to look up data but based on the key being the hash of that data. So you already know that the content exists, you know you have it, and you just have to go get the actual content. So with all that in mind, and all of these examples of ways you can use Git for something other than software, I'd like to present the case study of using Git for software. No, really. But the key detail is I don't just want to use Git for software source code. What I want to use Git for is all the binaries, all the build scripts and packaging, and all of the build dependencies recursively. For what it's worth, this software is called Aptors. The code is not posted quite yet because I thought you might prefer to see slides at this conference. And so I will be announcing the availability of the code somewhat later on the conference list as soon as I can. So the motivation for doing this was primarily getting sick of bugs with dependencies. This is a selection of relevant snippets of Debian changelog messages that are all bugs in some kind of dependency. So you have miscompilations due to optimization. You have miscompilations of things as simple as a right shift. You have optimization problems, you have hangs and seg faults due to XSLT transformations, you have versions of shared libraries, you even have cases where just you had all the right dependencies, but you also had NVIDIA packages installed and that broke things. So you had too many dependencies installed. And just to give an example of how prevalent these are, I just looked at one case here of your most common dependency is GCC. So I went to GCC's Bugzilla and searched for, they have keywords to categorize bugs, and they have a keyword wrong code. This is the really scary one. This is, I compiled valid code and got bad machine code with no compiler warning telling me of that. So this is where you get a crazy bug, and it's that 1 in 100 times when it's really not your code, it's the compiler. That kind of gives you the shivers. So I did a search for that actually about a year ago, and what I got was that lovely Bugzilla error message. 4,487 bugs found. That's a little scary. And the problem with bugs and dependencies, and the reason why I care about this so much, is that Git has a lot of tools to help you find bugs. And the really common case is that you've got a bug in your own code. So you've got a tree that looks something like this. Well, it's not a very interesting tree. You've got a line that looks something like this. At some point, you broke things, and then it was bad. So you want to find the point where it got broken, and there are awesome tools like git bisect to help you do that very quickly, even for very tall lines or very broad trees. You can find, and the problem is that what happens when you have dependencies? Well, you don't have a graph that looks like this anymore. What you have is graphs, plural, that look like this. And all of these are dependencies that are interrelated somehow, and you have a bug somewhere in some commit of one of them. Or you don't even have a bug, you just have a change in behavior, or something changed in one of these, and all you know is that you rebuilt with today's environment and it doesn't work, but it worked yesterday, and I don't know what went wrong. So this is the point where you start looking at your dpackage logs and see what package you last upgraded, or you try to figure out what changed on your system, or you go restore from backup, or you build it on Bob's machine because it works there. This is not a scalable solution, and it really is a pain and a drain on your time. So when you have a pile of repositories, there are some nice tools to help you manage them. There are multi-repository management tools like MR and Repo, and these are used when you have several hundred repositories or 1,000 repositories to manage, which is common when you've got a whole distribution like Android or Chrome OS. So these solve the problem of I need to git clone 400 things, or I need to update 400 things, some of which have patches I need to rebase on top of whatever upstream now has. So they solve that problem nicely. What they don't do is help you build the whole system that has those 400 repositories in them. For that, you have to stack something else on top of it that effectively gives you a distribution. So the goal of this system was, I want to have completely reproducible builds at all times, including a full history of reproducible builds. And I don't want just dependencies that say greater than or equal to version 1.2. I want dependencies that say this git hash and only this git hash. And if I want something else, I will change the hash, because I don't want to say that it works until I've tested that it works. So let's go back to those signs that, that you should use git. Well, here's some reasons why this build system should use git. Obviously, I've got some notion of versioning. I've got thousands of things with versions all over the place. I've got a lot of benefits from deduplication and delta compression, because not only am I storing source code, which already deduplicates like crazy, I'm storing binaries, which are usually similar over time, and not to mention any data files other than source code that I've got in my source nicely deduplicate against the exact same binary copies of those that are in my binary package. I often need to move these things around, either because I'm doing distributed development of the source code, or because, hey, why not use this as the distribution mechanism for your binaries? The track data is not insanely huge. Well, binaries are large, but they're not so large that Git really throws up over them. You're not doing any complex queries, because the most complicated thing you do is go give me this dependency by this hash. And I definitely have a use for content addressability. I use it to go find my dependencies. So I've gone through the why here of why I want to build this build system and why it should use Git. So now I want to cover the how of how it actually uses Git under the covers. So like I said earlier, the very first thing you want to do is figure out how your concepts map onto Git. So all of the content here is just trees of blobs. Whether it's your source code, your binaries, your build scripts, it's fundamentally directories of files, so it's trees of blobs. Revisions are commits, that's a given. And any cached build results you have, if you've run a build before, then you've taken a pile of dependencies and you've taken your build scripts, you've run it, and you've popped out with a tree, because your build result is fundamentally a directory of files. So then, what do builds depend on? Well, you're going to need your source code. You're going to need your binaries for all of your dependencies so that you can run your build, and you might need other builds potentially as part of it. You may need to import some common tool, or you're going to want to run the system recursively. So your build for glibc is going to depend on your build for the kernel headers and your build for GCC. You want to recurse these scripts all the way down. But as far as the build system is concerned, saying that you depend on source binaries and other builds is another way of saying that you depend on commits, commits, and more commits. It's nice to be completely oblivious to your content. So dependencies then are just one tree in your build script repository that has a blob for every single dependency, named for whatever you want to call it, containing just one 40-character line with the hash in it. So now all you have is this giant key value store in each dependency that says, okay, here are all of the things that this build needs in order to actually build. So now that you've got the mapping to get objects, when you actually do a build, all you're really doing is transforming one Git tree to another Git tree by running an arbitrary command. So you start from a checked out Git tree, you run an arbitrary command, and you record the Git tree you get when the command exits. So the nice thing about this is if you have an identical tree and you have an identical command you run, you should get an identical result. Now there are some real world cases where that doesn't exactly work because you can do crazy things like embed date stamps into your code or use randomness in your build, and if you're doing that, please don't, by the way. But especially here with this system, one thing I'm hoping is that you don't really have a strong reason to say, oh, this build was done on this date by this person to identify your build, because a much better way to identify your build is, oh, it's this build with this hash. So that works nicely. So you've got all of your builds, and since every build you do can be cached, because it's identical trees to identical commands give you identical results, then you can just pretend every single time that you're building from scratch. You could rebuild, quote unquote, all of Debian, but really, since you built it the last time that you had a supercomputer available, then you don't need to do it again. You'll just rebuild, oh, I changed this one package, so it and its whole dependency chain get rebuilt, but nothing else. So the actual build environment, the trick here of what do you do when you take a tree, run a command, and get another tree, right now it's a change root because that's the simplest thing to deal with. What I'd like to do is get much better isolation of builds because, for example, a change root does not isolate you against kernel changes. And it is entirely possible that a build that works under kernel 3.2 will fail under kernel 3.7. And you'd have to do a little bit of a stretch to have your build system exercise obscure bits of the Linux kernel API, but it is possible. And the better isolation I've looked at is using something like KVM with the 9p file system. It's a hostfs style file system that you can point at a directory. That would work really nicely, except it's incredibly slow. And a kernel build that would take about 20 seconds on a host machine will take several hours inside 9p just because the latency is tens of milliseconds per file. So that's pretty awful. I'm still looking for a better solution there. Suggestions are welcome. Now, one other fun detail is I needed some way to script my builds, and I want builds to be reproducible. That's a design goal. So I can version all of my language's libraries because, hey, those build scripts are in the repositories, so I can hash them and depend on them. And if I need a new version, then I can depend on a newer version, or I can use the old version. But what I can't easily version is the language interpreter itself because that's what's actually interpreting the build script. So there's a bootstrapping problem there. So what I need is a language that I can reasonably believe will be forward compatible forever. And I also need a language that has fairly minimal language features, but a very extensible language and libraries. Now, what language comes to mind when you're thinking of the smallest possible language with arbitrary extensibility and libraries? Lisp, right? So specifically, I ended up using Scheme as my implementation of build scripting because I needed this system to be more obscure and get fewer contributions. I'm already writing it in Haskell, but I don't think that's obscure enough anymore. I've run into so many people at this conference that write Haskell. So I had to make it more obscure. I need fewer users. So seriously though, these scripts are all written in Scheme, and they can, obviously then you can define other things like macros or language features in libraries, import them from other builds by hash, which means the whole Scheme standard library is stuck in a particular version of one tree with a hash, and you know that you can always build against that version rather than whatever newer version might have broken something. So I've added relatively few built-in functions to this particular scripting language. I've got a total of 5. One is the ability to run a build. So you take a tree, you give it a command with arbitrary arguments like configure -- enable awesomeness, and then you get back a tree. You can import a tree, which just means that tree actually contains another build script, so go load the build script in Scheme from that tree, run it, and the result of the import command is whatever that script returns, which in general will be a built tree, but you could also put a function in there. You can merge trees, so you take an arbitrary number of trees and you combine them together, and if there's ever a merge conflict of any kind, other than these files are identical in both, so I put them together, if there's ever a merge conflict other than that, then it just stops and fails. Or you can extract a subdirectory or add a prefix to a subdirectory. So this is really handy when you're doing builds because you want to pull out wherever you put your build result. So a typical build script looks a lot like this, and read it from the inside out. You're going to import a pile of dependencies like GCC, libc6dev, and make. You're going to take something like a standard build script, and you're going to pull in your own source code, which is a dependency that doesn't necessarily have to live in the same repository as your build script. You're going to merge all those together into one Git tree, and your source is prefixed with /source here so that it's separated from all of your dependencies. Then you're going to take that and build the result. And I'm assuming, I just wrote /build here. That could be a script that comes from dep standard build, but you could just as easily run configure make install with destdir or whatever. I'm assuming that build here installs to a /target destdir. So all of your installed binaries and man pages and whatever else end up in /target. So then you just extract /target, and that's your build. Most scripts are going to look a heck of a lot like this. You might have a few extra build steps if you're going to do a particularly complicated build, but you're not usually going to do something much more complicated than this. Now, it is obviously a Turing-complete language, so do whatever crazy thing strikes your fancy, but build script should probably not be somewhere where you're trying to be particularly creative. So there's one other case I want to cover is the interesting case of bootstrapping. This is something that comes up in Linux distributions as well. What happens if GCC depends on GCC? Well, the nice thing when everything is versioned and covered by hashes is that it's not actually true that GCC depends on GCC. What's true is that GCC-in depends on GCC-in-1. So you need a copy of GCC to build GCC, but it doesn't have to be the same copy. That's good because the way this system is built, you can't depend on yourself. That would be, again, a bit of a chicken and egg problem. So I'm using exactly the same solution that you use in Linux distributions. Take a copy of GCC plus whatever other tools you need for a bare minimum environment, effectively a decent chunk of the contents of apt-get install build essential, and you check it in as a binary and stash the source code away somewhere so that you'll be able to satisfy GPL obligations. And any other self-hosting tools you need go into that initial bootstrap, and then you'll just depend on your bootstrapped binaries in your first round. Then once you've got all those built, you can update the dependencies to depend on the versions you've bootstrapped away from that, and then you never touch those again, but they stay around in your history so you know what you built from. Now, it's interesting to note that the set of tools that are self-hosting is kind of surprising. Make does not actually depend on make. They were smart enough to say, hey, you might be getting make for the first time, so we'll give you a shell script that builds make from source. So that's kind of nice. Of course, you need a shell, but and a shell needs make. Oops. On the other hand, here's one you would not have guessed. Diff does not build if you don't have diff. And the reason for that is that diff uses auto tools, and configure scripts use diff. There are a lot of tools like that. In fact, a lot of the self-hosting tool loops pass through autoconf because it uses a lot of things for something trying to be so portable. So yeah, you'll end up with a decent chunk of binaries, but you can bootstrap away from them nicely. And for anybody who's seen the lovely paper, Reflections on Trusting Trust by Ken Thompson, the summary of which is, let's build a compiler that automatically compiles the login program to have a backdoor, and then compiles the compiler to have a backdoor inserter, and then throw away the source, and you have a compiler that reinserts its own backdoor and you never see it. Well, the nice thing about that is with this system, you can't do that unless the very first one you check in as a binary is that broken trust-breaking compiler, because otherwise you've got a full history of exactly what you built with what recursively back to those original binaries. So there's no way that you could first build a compiler that puts the backdoor in and then rebuild with that compiler without tracking that in the system. So I want to revisit one last time the reasons you might want to use Git programmatically, and I would highly recommend doing it. So map your content on the repository internals. Remember to use the built-in versioning for some useful purpose. Store your data in a way that works well with deduplication and delta compression. Use Git when you want to move and sync bits between repositories. Think of it as a giant key value store, because that's really what it is. And try to look up content by hash whenever possible. So I'm hoping that you all have plenty of good questions, but just in case, I want to throw in a little bit more controversy by saying, why is it that ftp.debian.org is not a Git repository? Wouldn't that be perfect? Store all the source and binaries there, use that as your syncing protocol, and then you can very easily deduplicate all of that data and deal with something. Instead of having a pool system, you just extract all of the files that you want and pull them down. You could even throw out things like documentation and man pages to save space as part of a filtering process. Use that to install. And with that little extra bit of controversy, now I'm hoping there are plenty of questions.
Josh, do you have any experiences or opinions about using non-standard refs, so something other than refs heads, refs tags, or refs remotes?
I do actually. So if you store things in refs heads and refs tags, then that's what the command line tools tend to expect, but it's not required. If you store in non-standard refs, there are still a few command line tools that will kind of not find your refs, but it will work. I have done several things with non-standard refs. In particular, I actually got a patch into upstream Git, which makes it so that you can have a subdirectory in refs, a set of subdirectories for different repositories, effectively sharing the same object store. So you can have refs, some subdirectory for a refs heads refs heads whatever branch, and refs some other subdirectory, refs tags this, and then you modify git receive pack, git send pack, and all of that, and you effectively have arbitrary repositories on the same object store. So does that answer your question?
You mentioned this build system based on Git. Is it available somewhere?
I mentioned that in partway in that it is in progress. It will be available in the very near future, but I biased in favor of getting my slides done.
Looks like we're out of questions. Thank you, Josh, for your speech. And